Okay, so the recording have started. So today we are going to, this is the third day in a row, the third Saturday in a row. The first Saturday we talked about energy audits and energy auditing procedure taken by Engineer Uche. And last week we talked about electrical and energy basics taken by myself. And today we're going to be looking at industrial energy efficiency. So when you go to conduct an energy audit in an industry, what do you do? How do you conduct energy audit in the industrial processes? So for you to do that effectively, you need to understand the industrial processes. You need to understand the steam system. You need to understand the boiler system. You need to understand the compressor system. You need to understand the air handling unit. So all those industrial processes, all those industrial equipment, we're going to be talking about them today, and that is the focus of our today's training. Hello, can you hear me? Hello, I need to confirm that I'm audible enough. Can anyone hear me?
Yes.
Okay, sorry. I think somehow I didn't even know when I got disconnected. I think that I had some little internet glitches here. I didn't know when this got disconnected. Please pardon me for that. So let me go back and start to share my screen again. Okay. Can you see my screen? I need response. Can you see my screen?
Hope you're recording again.
Thank you for reminding me that. Let me confirm that the recording is okay. Yeah, the recording is on. It's still recording. But just to confirm, let me stop and start the recording again. Let me just pause, stay recording. Okay, so thank you very much. So this is the point where I think I got disconnected from the internet. So I was trying to describe what energy efficiency is. So energy efficiency, most of us are already familiar with this, so I will not stress much on this. Energy efficiency is the practice of using less energy to do the same amount of work, or using less energy to provide the same quality of service. Using less energy does not necessarily mean reducing the quality or quantity of work that is being done. But in fact, if there's a way to improve the quality or the quantity of work that is being done, but using less energy, that's even super good. So examples include replacing a 60 watts rated incandescent bulb with 12 watts rated LED bulb. This is a classical example of what energy efficiency is. As we proceed, we are going to see the difference between energy efficiency and energy conservation. They are related, but they're two different things. And a lot of times we have mixed them up. So to enable citizens to understand energy efficiency better, many countries have introduced energy efficiency labels and ratings. So the next slide is going to be showing us some pictorial representation of energy efficiency labels. So here we are. We have Energy Star. This is very common in North America, Canada, and some of those countries in those regions. Then we have energy efficiency. Okay, we have an energy efficiency label, although it's not very common, but we have it, and it's already developed. We have the one of India, and we have this one that is very common in Europe. So energy efficiency labels are logos or ratings used to designate or describe the energy consumption characteristics of a device or system. In some, when you see some televisions from maybe from Europe or from America, you will see it clearly how much energy the television is going to consume if you use it in a year. Okay, so that is just to communicate to buyers when they want to purchase this equipment, just to communicate to them how efficient this equipment is. So in some countries, so like this last logo here, they use bars to represent how efficient. I already talked about this. So these designations from trusted agency means that the appliance exceeds minimum energy performance standard, usually by a significant amount. Products without these labels are most likely inefficient in in energy consumption. So interestingly, like I said, in Nigeria, we already have minimum energy performance standard, but I think it's still limited to air conditioning systems and maybe refrigerators in Nigeria. It's still not very common. So you might not, it has not been commercialized or, gone into the market. So some of the logos are what you're already seeing. So now, when we talk about energy efficiency, we need to understand the primary causes of inefficiency, because if we don't understand how this inefficiency comes into the energy system, then it becomes difficult for us to actually control the inefficiency. So we need to understand how these inefficiencies come into the systems, and by so doing, we can now be able to implement measures. So energy inefficiencies are induced by two primary factors. One of them is the human behavior, and the other one is technical losses. Okay, so to help us understand this, we look at energy balance equation. Energy balance equation simply means energy that comes into a facility or into an industry should equal to the energy that goes out from that building or the industry. Of course, we remember that energy can neither be created nor destroyed, but can be transformed from one form to another. So meaning that if energy comes into a building, it cannot suddenly be consumed, it cannot suddenly be destroyed. It can only be transformed from one form to another, and we need to understand how this energy lifts the building. I think I have thrown a bit of light into this. Most times, energy lifts the building in the form of heat, and that's why it's very important we understand heat flows, heat transfer processes. We talked about this in our last class. So if you understand this, you'll be able to see opportunities where you could recover some of those waste heat and then put them back into the industrial process. So let us break that formula down a little bit. So energy that comes in is equal to the energy that is used fully in the industry plus losses. Now we'll talk about the losses. We're talking about the technical losses. Now these technical losses are the energy that are used to overcome resistance forces. When I talked about electricity, I told you that electrons flows through the wire. Now those wires have resistances, okay, which are measured in ohms, right? So in overcoming those resistances, you have losses. The wire sometimes gets heated and it's converted to heat and it's dissipated into the environment. So those are technical losses, which you cannot totally avoid, okay? But there are also other losses in the system where energy is being consumed, but it is not doing any meaningful work. Those are wasted. Okay, so for example, let me use a very typical example in our homes. During the broad daylight, you have some security lights or the surrounding lights, leaving them on during the day. Yes, energy is being consumed, but is it doing any meaningful work? No, it is not doing any useful work. So in that instance, it is being wasted, but energy is consumed. But if you change that scenario and then put it at night when everywhere is dark and you switch on that light, then it becomes useful. Energy is consumed and it is consumed usefully, right? So that is the various ways in which energy leaves a facility. So we need to understand them. But again, we need to pay close attention to this energy that is being used, but it's wasted. And that is where human behavior comes in. So in energy efficiency, whether in industry or in our homes, we have to first of all make sure that we try as much as possible to eliminate or reduce as much as possible the human behavior, energy waste that comes as a result of human behavior. Then we can now also look at the technical losses. Like I said, you cannot eliminate technical losses, but they can be reduced significantly to the barest minimum. So how our energy consumption being calculated? In other class, I also talked about the difference between energy and power. And I told you that the difference is a function of time. So energy is power times time, right? So power, of course, we know is a capacity to do work, right? So, and then if you multiply that over time, that is the hours you use that capacity to do work. That's when you now have your energy. So there are also two ways to reduce your energy consumption. Remember, energy is equal to power times time. So the product of these two things will give you your energy. So what that means consumption. So how can you reduce your power consumption? How can you reduce your power? How can you reduce your time of use? If you're able to reduce any one of them or both of them. So reducing power needed to achieve the same result is equal to energy efficiency. Now, this is when if you're able to reduce the power. So for example, a typical example is what I said earlier, when you change your incandescent light bulb to an LED bulb, okay, you have reduced the power, but you may not have reduced the hours of usage, okay? So when you change your light bulbs, now these are just very basic examples. We are going to go into industrial equipment, industrial processes, but if you understand these basics, then it won't be difficult for you to also understand it when we start to talk about the industrial processes. So if you change your incandescent bulb to an LED, you reduce your power, not the hours of usage, right? But imagine that when you also change your incandescent light bulb to an LED bulb, and you also reduce the hours of use. So maybe you usually leave the light on during the day. Okay, maybe for example, you use that light bulb for 12 hours in a day, and you change it and you now reduce it to 8 hours. By reducing it from 12 hours to 8 hours, you have also reduced the hours of usage. So in this case, you have actually achieved what we call energy conservation. So energy conservation means that energy is not being consumed at all. You eliminate the need for energy. That's when we talk about energy consumption, energy conservation. But when we talk about energy efficiency, it means that energy is still being consumed, but at a reduced rate, right? And that's when we talk about energy efficiency. And these are just the two, this is just the difference between the two of them, energy efficiency and energy conservation. So what is efficiency? How do we even measure efficiency? So efficiency is measured by useful energy that comes into the place, useful energy divided by the total energy that comes into the place. The one that you use usefully divided by the entire energy that comes into the place. That is how we measure efficiency. So useful energy divided by the total energy input is how we measure efficiency. And of course, how do you calculate the useful energy into the system? Okay, so it is energy that comes into the process or into the facility minus the losses. Now we are talking about useful energy. It's energy that comes into the building minus the loss. Now these losses, like I mentioned earlier, are two kinds. You have the human factor and then you have the technical factor. So both factors are considered here. So the entire energy that comes in minus the losses divided by the entire energy that comes in, that will give you the efficiency. efficiency, either in percentage or in 0 points, whatever figure you're going to get. Okay, but for you to really do efficiency in any system, your system boundary has to be determined. You need to define your system boundary. Okay, so when you got to do an energy audit, you need to be clear on the scope of your audit. What are the boundaries of your audit? You could do an audit for a particular industrial process. Okay, you could do an audit for entire industry, which means it has so many processes. Okay, you could do an audit for a particular unit. So you have to define your boundary. So when you establish your boundary, you have to now find out all the process, all the means through which energy comes into that boundary, and all the means through energy leaves that boundary. Okay, you can now begin to now see where losses are coming from and how you can also be able to recover some of the energy losses and put it back into the system so you can reduce the amount of energy that need to come into the system in the first place. So let us jump right into the industrial energy applications, the energy efficiency applications in industries. And the first thing we're going to talk about is combustion. So combustion is the first thing that occurs when you're converting from chemical form of energy to thermal form of energy. So you have to do combustion. It's the first, and most of the energy that we use today, most of them are primarily, they come in the form of chemical. So for example, you have your fossil fuels, those are chemical forms of energy. And for you to realize the energy inherence, the energy that they contain, you need to first of all burn them, split them up, and then by burning them, you have your thermal energy. So let us look at the process of combustion. What are the inefficiencies that could occur when you're doing a combustion? What is actually a combustion? So combustion is simply a chemical process. Remember, I told that most times you start from a chemical form of energy, whether you're fossil fuel, petroleum, PMS, diesel, gas, coal, all of these are chemical forms of energy. So you start with combustion. So like I said, combustion is a chemical process of converting hydrocarbon fuel to thermal or heat. Okay, so if you look at this equation we have here, we have CH4. This is a hydrocarbon-based fossil fuel. Then you have oxygen in the presence of oxygen. So combustion is a fuel. Like I said, it's a chemical reaction of fuel in the presence of oxygen. It combusts. It's kind of plus heat. It's actually three things. The fuel, which is the petrol or diesel or PMS or whatever, or gas. Then in the presence of oxygen comes in with air. Okay, we're going to talk about air, how you introduce air into the combustion system, and plus heat. You notice that your vehicles, okay, they need spark plug. What does spark plug do? Spark plug introduces that heat for combustion to happen. So spark plug ignites it, right? So if there's no heat, if there's no high temperature, there will not be combustion. That's when you have your gas. When you strike your gas, for some of us that have automatic gas, when you strike it, there's something that ignites it, something that introduces heat for the fire to start. If your gas is not automatic, you need to use match or lighter to add that heat for it to start. So that's combustion for you. And what are the products of combustion? We have carbon dioxide. This is the product of combustion. Then we have water, and water that comes out is not the kind of liquid water that you see, but these are water vapor, right? They're in the form of gas vapor, and then you have heat as a product of that combustion. So what we usually take from this combustion process is the heat. We take the heat and we transform it into another form of energy. So for your cars, you take the heat, you transform that heat into a mechanical form of energy, which is the drive, your pistons that moves, and then your pistons now moves your vehicle, which is the mechanical form of energy, and it moves your vehicle. Okay. So this is combustion process. We're going to see how we can criticize this combustion and find ways to improve energy efficiency in this combustion process. So look at these flames. We have about 4 kinds of flames here, okay? Starting from the number 4. Number 4 is the most efficient combustion process, and number 1 is the most inefficient combustion process. So if you have this kind of flame, it means that if you have this kind of combustion or this kind of flame from your combustion process, it means that you have high level of inefficiency. But if you have this, then there's a high level of efficiency. And this is a typical example of your gas burners. For good gas burners, this is what you have. For people that uses firewood, this is what you have. It's highly inefficient. Okay, so now combustion can be complete and it can be incomplete. So the whole idea for us as an energy auditor is to make sure that a combustion process is complete. Because if the combustion process is not complete, it means that you have unburnt fuel. There are fuel that should have opened up and released their energy that are not, combusted. So they leave as waste. So we need to make sure that the combustion is complete. How do we make sure that the combustion process is complete? We need to introduce excess oxygen. If there's no right amount of oxygen in that combustion process, it will not be complete. And once a combustion is not complete, how you know that a combustion is not complete? That now there's what we call combustion analyzer, because some of these gases you cannot see them by your physical eye. So you take an instrument, you measure it, you measure your output, that is your flue gas of your combustion process. Once you notice there is carbon monoxide, CO. Remember, our carbon dioxide is CO2, but carbon monoxide is CO. Once you notice there is CO, it's a clear indication that is an incomplete combustion. Okay, so if you have a complete combustion, you will definitely see, okay, the flame will be blue, there will be no residue, the temperature will be high, and of course, higher efficiency. But when you have an incomplete combustion, you see something like orange or yellow flames, you see black residue, smoke, and you see the temperature, of course, is going to be low, and energy is wasted, and you have a toxic gas, which is the carbon monoxide that I talked about. This is a clear indicator that tells you that, look, the combustion is not complete. So I have already talked about what is complete combustion. To ensure complete combustion of the fuel used, combustion chambers are supplied with excess air. Excess air increases the amount of oxygen to the combustion and the combustion of fuel. I've already talked about this. So when we achieve a complete combustion, meaning that the air and the fuel are in perfect balance, okay, when we achieve this, the combustion is called stoichiometric. Stoichiometry. This is just a scientific word. So the combustion efficiency increases with increased excess air, but we have to take caution. Now, until the heat loss in the excess air is larger than the heat provided by the more efficient combustion. Now, what this is trying to say that even when you're adding excess air, you need to be careful. You need to do that with caution. There is an extent to which you add excess air, it will begin to be counterproductive. It will also begin to reduce the efficiency of that combustion process. So there is just slightly higher amount of excess air that you can add, depending on the combustion fuel that you have. So here is some of the examples. If you're using a natural gas, it is recommended that you add between 5 to 10% excess air. Okay, if you're using a natural gas. If you're using fuel oil, if you're using diesel or PMS, you can add excess air of maybe 5 to 20%. If you're using coal, you might add excess air between 15 to 60%. All right? And this is just a diagram to illustrate to us how that relationship happens. So at this point where you have a slightly shaded area, that's where you have the highest efficiency. Okay, you can see the efficiency begins to drop. If it begins to add excess oxygen, this efficiency begins to drop. Okay, and then this is the fuel. At this point where you have the fuel, you have the highest efficiency. But if the fuel, okay, now this is excess fuel. If you begin to increase the fuel beyond what is required, the efficiency also begins to drop. So this is just a diagram to illustrate the relationship between all of these combustion elements. So like I already mentioned before, to measure the combustion efficiency, you need what we call combustion analyzer. So here is a picture of what we call combustion analyzer. And this combustion analyzer will tell you if there is complete combustion or incomplete combustion. So if you notice the presence of carbon monoxide, nitrous oxide, sulfur oxide, now all of this will tell you is an indicator that is an incomplete combustion, but chief of them is this carbon monoxide. It tells you, look, there are fuel that are not being burnt in this process, or it does not achieve complete combustion. So now we've talked about combustion. Where are the areas in which this is which this takes place in industry? So it happens inside a boiler. Okay. So when you see a boiler in an industry, just know that there is a combustion that is going on inside that boiler. So the boiler, depending on the feedstock, on what you're using to feed that boiler, it could be gas, it could be diesel, it could be it could be biomass. Okay, yeah, it could be any hydrocarbon-based fuel that you're putting into that boiler, and then there's a combustion that is happening inside that boiler, and in the end, what you get out of that combustion process is heat. So that heat is now transferred into the water, right? So when the heat is transferred into the water, the temperature of the water rises. When it gets to 100, it turns to steam. Okay, and then you take that steam, you now take it out to your industrial process. We're going to come to that. You're going to come to steams, but now let's focus on boiler. So there are basically two kinds of boiler, basically two types. So boilers are needed to generate steam, like I've already explained, and steams are heat carriers. The same way you have wires in your street that carries electrons, right? That's what steam does. Steam carries heat, across industrial processes to the point where you need them for an industrial process, okay? So there are two basic types of boiler, and it's very simple. You have the water tube boiler, and you have fire tube boiler. Now, as the name implies, when you say water tube, it means that water is passing through the tube. Look at this boiler here. Water is coming in through this pipe, and the water is flowing through the tube, and it's also leaving. So before the water passes through this grill or this tube here, as the water is passing through it, this fire is heating the water, and before it gets to this place, it's already turned to steam, and the steam leaves here. So it comes in as a liquid and it goes out as gas. So this is water tube boiler, and then this is fire tube. As the name implies also, the fire is now passing through the tube. So you have something like a drum of water, and you're passing heat, through the tube, and it's heating the water, and the water is converting to steam, and it's coming out as a steam. Okay, and after the combustion process, what comes out here is hot gas. So this is what we call flue gas. What comes out here is what we call flue gas. Okay, so you will notice that the gas that is coming out here is always, essentially it is hot. It's very hot, right? So like I told you, most time the energy that comes into the building, they leave those buildings in the form of heat. So this is a classical example of how those energy leaves the building in the form of heat. So the question, what can we do to recover this waste energy that is going out from this flue gas, right? We will come to that, how we can recover waste heat. We are going to talk about how we can recover waste heat in boiler systems. So this is the transformation that the water go through. When you bring in water, you heat it, assuming your water is at 25 degrees centigrade. When you heat it, when it gets to 100 degrees centigrade, it begins to change and begins to turn to gas. That's when it begins to turn to steam, and from there it continues. So at this point, the energy that is being expended here is latent heat. Okay, but to raise the temperature from 25 to 100, you need sensible heat. Okay, I explained all of this in our last class. So I'll just move ahead so we can be able to cover all we need to do. So now there are equations to do heat calculation, heat transfer calculations. Okay, and just like I mentioned now, you have sensible heat and you have latent heat. So you have different equations for also calculating sensible heat and latent heat. And it's very important that you understand when it is a sensible heat and when it is a latent heat. If you have that understanding, then you know the equation that you're going to apply. Like I said in the last class, someone's mic is on and it's disturbing the class. Please, can you mute yourself? Please just do that, because it will take me some few seconds to mute everyone from my own end. So just please help us and then mute yourself.
There's no doubt raising money.
Uche, I think that's you. Uche, please mute yourself.
It is account. Today
Oh my goodness. Okay, let me see how I can do that from here. Okay, so I have just done that. So as I was explaining, you need to understand the form of energy. Oh shit, someone else mic is on. Please, let's just play by this simple rule so we don't interrupt the class. Leon, your mic is on. I just need to mute you now. Okay, so let's continue. I think we can have a more serene environments to communicate now. So, as I was saying, you need to understand the form of energy that's taking place in the form of heat, right? So you can know the right formula to apply. I said this in the other class that you don't necessarily need to cram these formulas. What you need to do is understand what is going on, understand the form of energy that is being transferred, and then you can pull the formula. You can look off to the internet, but make sure you're using the right formula, even if you're pulling it from the internet or from any textbook. So we have different kinds of formulas for heat transfer. We have the first one is for sensible heat only. Sensible heat. So if you're dealing with latent heat and you apply this formula, you're wasting your time. You get the wrong answer. So this is for sensible heat, and the M here is mass flow rate. You know, when you're talking about sensible heat, you're talking about temperature of water. So water, what's the mass flow rate of the water? You're talking about the specific heat capacity, that is the CP. You know, specific heat of the water. It's always a constant value for water. Then you have the temperature difference. From what temperature to what temperature are you heating the water? So that's what, and the units, when you do all this your calculation, the unit is coming out in kilowatts. When you're dealing with something that has to do with both sensible heat and latent heat, you know, a combination of both sensible heat and latent heat. So you use this formula. This is still mass flow rate because you're talking about sensible heat as well. But again, you're not talking about latent heat. So which is, in this case, you're talking about change in enthalpy. So DH is change in enthalpy, okay? But when you're dealing with, okay, yeah. So now this is heat flow through a surface. Heat flow through a surface. If the sun is out and you want to calculate the amount of heat that comes into a building through the wall surface, this is the kind of equation you use. If you're heating water and you want to know the amount of heat transfer from the fire to the water, okay, through the surface, through the kettle or through the pot or through the medium through which you're heating, this is the equation that you need to apply. Okay, but if you're calculating the temperature rise in the water, maybe you want to heat the water from 25 degrees centigrade to 80 degrees centigrade, and you want to know the amount of heat, you're going to use sensible heat. If you're calculating the heat transfer from the fire to the water through the surface, you use this heat flow through a surface. If you want to calculate the heat transfer when the water is hot, maybe you're heating from 100 degrees, no, you're heating from 80 degrees to 150 degrees. You know, at 150 degrees, the water is already gas. So you use this middle equation, which is sensible and latent heat. So you need to understand, and these terms has been defined here. Like I say, the Q here is heat flow, and the M is mass flow rate. The DT is change in temperature, CP is specific heat, and then you have change in enthalpy, and then you have your coefficient of heat transfer, which when you're talking about heat through a surface. Then you have your area of the surface.
Hello, excuse me, please.
Okay, okay.
Please, when do we talk about we talk about sensible heat? When do we talk about latent heat alone? Is there any time to calculate latent heat alone?
Yes, thank you very much. Yes, thank you very much for the question. There are situations where you also talk about the latent heat. So assuming you're heating from 120 degree, okay? You're heating from 120 degree to 200 degree. Then in that case, you're talking about latent heat. You're not even talking about sensible heat. It's mainly latent heat you're talking about. Okay. So in that case, you still use this middle equation, the one in the middle. Yeah, you still use it. There is what called there is a table. I'm trying to remember the name of the table where you can actually get its properties of steam. I mean, the table is actually a property of steam. So at every temperature and pressure, you'll be able to determine what the enthalpy would be. Okay, so if they give you the question, sometimes either they supply you some of these details or you need to consult this table, property of steams. You need to look at those tables. At what temperature is the steam? At what pressure is the steam? When you look at the temperature and pressure of the steam, you follow you follow that table, then you can be able to find out what the enthalpy is at that temperature and pressure. Okay, so let's continue. We'll get to that. So thank you for bringing that up. So we have energy conversion table. So this is just an energy conversion table. This is just a guide, right? So if you're converting from one form of energy to another form of energy, so if you have maybe 1 meter cube of natural gas, okay, and they want you to leave your answer in a megajoule, so this table will help you do the conversion. If you have 1 liter of gasoline and you want the answer in megajoule, this table will help you do the conversion. So these are just different forms of fuels, and you know what their energy content in terms of megajoule or gigajoule is. So this is just an energy conversion table. We might be needing it if we need to solve examples. So here is just a quick question. Heat, which when added or subtracted does not result in change of temperature, is called what? It's called what? Heat, when added, it does not, if you add the heat or you remove the heat, it does not result in change in temperature. What kind of heat is that? Just one person to respond, please. We'll move ahead. This is a very simple question. This is a bonus question. If you find this kind of question in your exams, then it's, now when I talk about exams, you know, when I make my trainings, 2 things are in my mind. It's either you're writing exams or you're applying this knowledge in industrial energy audit. Okay, so that's why sometimes when I thought I have to relate it back to industrial process, and some of them I have to relate it back to if you're writing your exam. So if you find this kind of question when you're writing your exam, it's just a bonus. But the truth is that you find some of this questions. So it's not always very difficult or hard question. Somebody has posted sensible heat in the chat. Who else? Let me hear from someone else. Heat, which when added or subtracted does not result in change of temperature. The temperature does not change. So it's a heat that is used to change phase. So when you heat a water up to 100 degrees centigrade and you keep heating that water, right? What happens? That water begins to change to steam, right? What kind of heat is that? It is not sensible heat. Somebody posted sensible heat. It is not sensible heat. Sensible heat is when you're heating the water from 22, or maybe the water is at 21 degrees centigrade or 25 degrees centigrade, and you heat it up until 100 degrees centigrade. That is sensible heat. But when you're heating it from that 100 to 100 and whatever it is now latent heat. It's no longer sensible heat. It is latent heat. Okay, so thank you very much for those who have posted an answer. Let's continue. Like I said, this is a bonus question. If you find this in your exam, it's a bonus question. So how much heat is required in kilowatts to raise the temperature of water flowing at 100 kilogram per hour? Now, 100 kilogram per hour is what? Mass flow rate. Water that is flowing at 100 kilogram. So in 1 hour, 100 kilogram of water passes through. That's what it means. And then you want to heat that water from 20 degrees centigrade to 100 degrees centigrade. What kind of heating are we doing? What kind of heating are we doing? At least sensible heat. So yeah, thank you very much. So I also want this to be interactive. In as much as I want you to mute yourself, but I also want it to be interactive. If you need to speak, unmute yourself and then speak. I want it to be interactive. Let me just know that you're following. Okay, so now, like I told you, sometimes if there are constant values that you need, they will provide you those constant values. Now, in this question, they have provided us with specific heat of water. This is the specific heat of, so it is 4.2 kilojoule per kilogram per degree centigrade. So what means that water, the energy that water can carry, and water is the element that has the highest, that can carry the highest amount of energy. Water is the element that can carry the highest amount of heat or energy per degree centigrade. Okay, so water can carry 4.2 kilojoule per kilogram per degree centigrade. So for 1 degree rise in temperature of water, it can absorb or release 4.2 kilojoule per kilogram of, that's what the specific heat of water is. Every other thing have them. If you're talking about diesel, if you're talking about air, they have their own specific heat capacity. But for water, water have the highest, 4.2. So this is the question before us. I will just run through it so that we don't waste so much time here. Okay, so like I already told you, it is a sensible heat. So this is the equation for sensible heat. Mass flow rate times specific capacity of water times change in temperature. So change in temperature is what? 100 minus 20. That is change in temperature. What is your specific heat capacity? 4.2. What is your mass flow rate? 100. So you put all of this in the equation, and then you have your answer. But you're having your answer in what? Kilojoule per hour. Now the question says you leave your answer in what? How much heat is required in kilowatts? Okay. Now your answer is in kilojoule per hour. So how do you convert this kilojoule per hour? You go back to that table that I showed you for conversion of units. Okay. So when you go back to that table, you see that 3,600 kilojoules is equal to 1 kilowatt hour. Let me just quickly go back to. So see, 1 kilowatt hour is equal to 3.6 megajoule. Okay. So if you're now removing this megajoule, maybe you want to do it in kilowatts, you have to multiply by 1,000. So it's 3,600, which is what we have here. 3,600 kilojoule is equal to 1 kilowatt. Okay. Now you divide both sides. Now, okay, so we have 3,600 kilojoule per hour, right? So this 3,000 kilojoule, remove this hour, 33,000 kilojoule, what does it give us in kilowatt hour? So if you do 33,000 kilojoule, you can cross multiply this 33,600 times 1 divided by 3,600. When you do that, you have 3,000, you have 9.33 kilowatt hour. Okay, so what you do now essentially is to remove this. You want your answer in kilowatt, not kilowatt hour. So you divide both sides by hour, right? So you divide both sides by hour. When you divide both sides by hour, this hour cancel this hour. So you're left with 3.33 kilowatts, right? So 3.33 kilowatt is equal to 33,600 kilojoule per hour. Okay, so I mean, it might look a little bit confusing for some of us, but please, you're going to have this document. You can practice it. I just wanted to run through this explanation, but practice it at your own time. If there are questions, you can always reach back to me. So let us look at energy losses in boiler. How does energy losses occur in a boiler system? Okay, we need to understand how this energy, so that when we go out to industry to do an energy audit, we can look at for those areas or those means through which boiler loses heat, and we can now begin to note them down and begin to recommend them in our recommendation. Okay, so let us look at that. So I have already mentioned that there is a heat loss through the flue or flue gas. After the combustion, there is a significant amount of heat that is lost through the flue gas. There is also heat in moisture content of flue gas, the same flue gas we are talking about. There is incomplete combustion. So you need to use combustion analyzer to first determine if the combustion of that boiler is complete or not. If it's not complete, we recommend maybe they add a slight more SX air to it to achieve complete combustion. Now there's what we call blow down water. Okay, you know that when you heat water and water evaporates, sometimes if there are impurities in the water, you will see the scales on the surface. So assuming you put 1 liter of water in a kettle and you have impurities in that water and you heat that water, once the water evaporates and turns to steam, sometimes you notice there are scales. You know, all those impurities will settle at the bottom of the kettle, right? So it affects boilers. When you keep adding water to boilers and evaporating them, they always have this solid residues. We call them total dissolved solid. You know, they begin to form inside that boiler. So over time, you need to flush out those solids, those impurities, right? So when you open the boiler, the bottom of the boiler, when you open it to allow those dissolved solid to flush out, heat is also being lost in the boiler system, because you're opening it to release hot water in the boiler with the dissolved solid. You want to flush them out, so heat is also being lost. So you need to recover that heat that is also being lost. So there are also radiations on the boiler surface. You know, when you're heating water, just like when you're heating water in your kettle, you notice that through the walls of the kettle, heat are being lost into your kitchen or the environment, heating environment. So there are also radiation losses, and there are combustibles in ash. So assuming you're using biomass for in your boiler, okay, sometimes you might know there are some combustibles in the ash that you need to throw away. And then there's also the heat loss in pack loading, okay? This might not be significant, but if you're not using your boiler optimally, of course, the efficiency will drop. But the chief of them is heat loss in flue gas, which is about 8 to 35%. Okay, so this is happening at the exit temperature or excess air. Okay, so we need to recover it. So the chief of them is this flue gas, so we need to recover it. We're going to talk about how to recover that. So let's talk about energy saving opportunities in boiler. So the first thing we need to do, we can do installation of economizer. Now I'm going to explain what economizer is. Economizer and recuperators are similar, but economizer is for water. Recuperator is for air. Economizer is using water to recover the waste heat. Recuperator is using air to recover the waste heat. In some cases, you have to use the two of them. You have to use both water and air to make sure you get all the heat that you need to get from that excess air, right? But you need to also be careful. I don't want to go into very deep technicalities of recovering heat in boiler, you know, so that I don't get you confused. You need to get to this level before I can now begin to talk about the next, but the one thing I want you to take away that you cannot recover all the heat in that flue gas. If you recover all the heat, you create problem in that boiler. So you could recover the heat up to maybe about 150 degrees centigrade. If you go below 150 degrees centigrade, something is going to happen in that boiler that could create problem for that boiler. But there are other forms of technology that could be used. But for now, let us just understand that we have to recover the heat from the waste, from the flue gas, okay? So so if you're using air, when I talk about recuperator, I say you're using air to recover the waste heat. You can use that air to reheat. Remember, you're adding air. Your combustion is a component of fuel, air, and then heat. So the air that is going into that combustion, you can preheat that air using the recovered heat. You know, you can recover the heat and then inject that air back into your combustion chamber. So that, you know, so just like introducing that heat back into the combustion system. And by doing so, you reduce the amount of fuel that you need to achieve complete combustion. I will explain that with a diagram. It might look ambiguous, it might look vague here. So we also have combustion control. We have blowdown optimization. I explained what blowdown is. We have installation and repair of insulation. We have load management. Then we have variable speed drive. I will explain that later. We have boiler replacement. If you have a very old and inefficient boiler, you might just need to replace the entire boiler. Then you have general good housekeeping. Now, let me explain what economizer is. Now, this is a boiler, and this is the flue gas that is going out, right? This is the chimney, this is the flue gas that is going out. After the combustion, the flue gas goes out. Now, what the economizer is that you have a pipe around the exhaust gas, and you pass water. You pass water around this pipe. Okay, the water absorbs the heat that should have gone out to the environment. So when you absorb that water, you now reintroduce that water into the boiler. Now, if you're heating water from 25 degrees to 100 degrees, you will use significant amount of energy or the significant amount of fuel. But imagine that water is already coming in at 60, or even the water is coming already at 70. So you're heating from 70 to 100. You're no longer heating from 25. And that is the benefit. So you recover this heat and reintroduce it back into the boiler. So by doing so, you reduce the amount of fuel that is needed to generate the steam. So this is what we call economizer. And if you're using air, you can also pass air around here, you know, to recover the heat, and you inject that air back into the combustion chamber, right? If you do that, you reduce the amount of fuel that you need to generate the required amount of heat to change your water to steam. Okay, so these are heat recovery processes. Now, this is economizer. This is recuperator. Like I told you, this is recuperator. In this case, you're using air instead of water. You're using air. Okay, I've already explained this. So this is a boiler checklist. Yeah, just if you go in, you can just take this to do a checklist on your boiler. Check efficiency, combustion. Like I already explained combustion for you. Check water, good water treatment. I already told you that sometimes if the water is not treated well, it will leave residues, scales inside the boiler, and it affects the boiler, which means you need to do a frequent blowdown to remove those scales, and those are heat losses. So repair water and steam leaks. So these are just checklists that you can read up. So let's talk about steam. Now, boiler is just to generate the steam. Boiler is to generate the steam. Now, let us talk about the transportation of that steam, which is the steam system. How do you move that steam from the boiler point or boiler plant to where you need it? Okay, so what happens? So that's what the steam system is about. So this is just now, the way you have your distribution network in electricity, the way you have your distribution network, that's the same way you have your steam distribution system. Okay. So that's what, so in electricity, you have your generator where you generate the electricity, you have your distribution system. It's synonymous to what we're doing here. Boiler generates the steam, you have a steam system that distributes the steam. Okay, so here we go. This is the boiler that generates the steam, and the steam leaves the boiler and it goes to an industrial process. Now the steam comes to a place where you need that steam to heat. Maybe you're producing something and you want to do pasteurization. Pasteurization is for example, if you're manufacturing milk and you need to treat that milk for safety and unhygienic purposes, you need to expose that milk to a very high temperature to kill whatever bacteria or whatever it is in the milk. So it's part of the process that is called pasteurization. So you need heat to do that. So, and one of the ways through which you can take heat to do that pasteurization is through the use of steam. So once you take the steam and you get to the point where you need to do a heat exchange. Now, what is a heat exchanger? Heat exchanger is something that absorbs the heat in the steam and transfers that heat to your process. So maybe if you want to pasteurize a milk, for example, heat exchanger is an equipment that takes the heat from the steam and transfer the heat to the milk. Okay, so that's what heat exchanger do. So, but once that happens, what happens is the steam will lose the heat. And once steam loses its heat, it goes back to liquid. Remember, we started from liquid, we heated it, it turns into a steam. Now, when you take away the heat from the steam, it goes back to becoming a liquid. And you need to remove that liquid from the process, from your industrial process. If you don't remove it, it will create a problem in your system. So you need to remove that liquid. So the process of removing that liquid is what we call steam trap. So we use steam trap to remove condensed steam. Now, when the steam loses its heat, it condenses. Condensation means that it turns back to liquid. And once it turns back to liquid, we need to remove it. So we use steam trap to remove it. And this is what we call steam trap. So steam trap collects the condensed steam, the water, and it sends it back. It sends it back to the boiler. Now, if you're sending it back to the boiler, sometimes you might need to pass it through the economizer, that is the exhaust of the boiler, to recover the heat, to increase the heat of the steam. Okay? No, sorry, to increase the heat of the condensate. We call it condensate. Then you now feed it back into the boiler. There are benefits of recovering your steam. I think there could be few industries that might be discharging this steam. They may just, the condensate, that might be few industries that will be throwing it away. So when you go to an industry and you find out that they're not recovering their steam, their condensate, then it's a good opportunity. You need to recover those condensates and feed it back into the boiler. One good thing about recovering condensate is that you don't need to treat the water again. Remember that the water that is coming into this boiler, your feed water that is coming into this boiler, you need to treat it to remove the impurity so it doesn't cause scale buildup. But if you're using condensate back into the boiler, you don't need to treat it. So it saves you the cost of treating fresh water into the boiler. So this is an added benefit of recovering your condensate. Okay, so this is a steam system, and these are industrial applications, industrial processes where you need the steam, and these are steam traps to remove the condensate, and it goes back into your boiler system. So steam system now in the whole steam generation and distribution, up to 40% of the heat are lost. Now, 20% of those are lost through condensate and flash steams. Okay, I already explained what a condensate is. Okay, and about 13 to 15% of them are lost during steam generation. Assuming you're recovering your flue gas, that's where you have. If you're not recovering your flue gas, you could have as more higher than this kind of losses in your generation, steam generation. Then your steam distribution, you can have up to 5 to 7%, but this is just for an indicative. These are just indicative values. So I've already talked about condensate recovery, right? When your steam is leaving your boiler, is leaving in the form of steam, and then you have your steam trap. When the steam condenses, it goes back into liquid. You have your steam trap that recovers it and then send it back to the boiler. I've already discussed what this about this. So this is condensate recovery. The benefit of condensate recovery. I think I've already also talked about this. The condensate water contains up to 20% of the steam energy. Returning this to the feed water tank preheats the feed water and thus lowers additional fuel input. So all of these ones are just what you can read. I have also explained what TDS means, total dissolved solid. Remember, I told you that condensate water does not contain total dissolved solid because they have already been treated. You don't need to treat them again. Thus, it reduces boilers blowdown cycles. I've already also explained this. So this is what a steam trap looks like. Okay, now steam traps are a type of automatic valve that filters out condensate. That is condensed steam and non-condensable gases such as air without letting steams escape. So this is what a steam trap is sometimes. Now, care needs to be taken when you go after an audit tool. You need to ask questions on the maintenance schedule of their steam trap. Now, here is the problem. Sometimes there might not be adequate maintenance of the steam trap, and two things could happen. We could have something that we call fail open or fail close. Remember how it works. A valve opens and allows the condensate to go out without letting the steam escape. Okay, but the condensate goes out. Now, sometimes the steam trap might open and fail to close. Okay, it's a mechanical system. Remember, it's a valve, it's a mechanical system. So sometimes it might open and it will now fail to close. What happens? You will now begin to lose steam. Steam will begin to flow away from that valve. Right? Sometimes it might also fail to open. It might fail to open. And once it fails to open, what means that you have a lot of condensate build up in your steam distribution system. And once that thing happens, there's what we call hammering effect. Okay, it can destroy your steam pipes, your steam distribution system. Okay, so you need to ask questions about their maintenance schedule of their steam trap. And based on that, you can now make a recommendation. Maybe they need to improve on the frequency of their maintenance of the steam trap. So steam system improvement, use high quality steam traps and establish a program for regular systematic inspection, testing and repair of steam trap. I already talked about this. Return condensate to the feed water. Now, sometimes you also have steam leakages in your steam distribution system. You could have steam. So when you see this kind of thing, in fact, this is bad. Some you might not be able to see it, but you might hear a whistling sound. Okay, you know that there are steam leaks. So these are areas through which energy have been lost in the steam systems. So you need to be able to pay attention. Sometimes there are instruments that you could also use to detect, very tiny, orifice in steam distribution system where leakages are taking place. Okay, so you need to detect if there are leakages in their steam system and it has to be fixed. So steam line installation, I have conducted an industrial energy audit where their steam lines were not insulated. And I was like, who did this installation in the first place? But I later found out that because when I asked questions, I got some answer, which I'm not going to disclose here anyway, but it is not a good thing, right? For your steam lines not to be insulated. Because these steam lines are carrying hot steams. If you don't insulate them, they will lose those steams to the environment. And they will lose the heat that they should ordinarily take into your industrial processes, meaning that you need to add more heating, add more fuel to bring them back to steam stage. So it's a very clear point to look at for in an industry. Look at their steam distribution lines and ensure that they are all insulated. If you look at it, this is before and this is after. So there is also an equipment that is called a thermal camera or thermal imager. So sometimes when you go and know this, you might use this equipment to be able to see hot areas. So these two images here are taken using thermal imager or thermal camera. So if you use a thermal camera, you can see that this place is hot, meaning there is no adequate insulation, right? So, and this is it here. And this is when it has been insulated. And this is it. When you use the same thermal imager to look at it, you won't see that hot area anymore. So I talked about heat exchanger. I already explained what heat exchanger is. So heat exchanger is what you use to, is an equipment that used to transfer heat from a steam to your, okay, this is a yogurt. I think this is a pasteurization process. Now, what comes in here is a yogurt, and what comes in here is a steam. So there is a heat exchanger that is wrapped around it to transfer the heat from the steam into the yogurt, and what comes out is a condensate. So this is what we call heat exchanger. So I'm not going to spend so much time on this. So heat exchanger recovery. So we use heat exchanger in economizers. We use heat exchanger in recuperators. You know, we also use heat exchangers inside the industrial processes. So these are just common sources of heat. Compressor, we are going to get to compressor. We are going to look at where heat losses are taking place in compressed air system. So you have flue gas. We've talked about flue gas. You talk about water, wastewater. You talk about oil jackets, Now these are all sources of heat, and these are common uses. What could you do with if you're able to recover some of this heat? What would you do with it? So first thing is preheating, drying, sanitary hot water, absorption chiller, heat pump, and all of that. So this is a checklist for heat recovery. You can read up this. I need to move to cover up all we need to talk about today. Now that's what we call pinch analysis. Pinch analysis is a concept. Okay, now remember, in industrial, most of what you're going to be doing or where you're going to be inspecting in an industrial process is either the addition of heat or removal of heat, that is subtraction of heat, or the mechanical movement. Note this about 3 things: addition of heat, removal of heat, or mechanical movement. These are the basic 3 things that you're going to be seeing in an industrial process. Now, when you talk about electricity, you find out that these 3 things I talked about now, didn't talk about electricity. Addition of heat is a chemical process. Removal of heat is a chemical process. Mechanical movement is a mechanical process. So, but you need electricity to either generate heat, remove heat, or do the mechanical movement. But the actual consumption of that energy is either removal of heat, addition of heat, or mechanical movement. Now, I want to narrow this to addition and subtraction of heat. If you go into an industry, in some places you might need to add heat. So, for example, if you go to a yogurt producing company, if they want to do pasteurization, they will add heat. But after the product has been produced, they will need to remove heat to bring it to a low temperature, right? So, in this kind of situation, there is an opportunity such that when you're removing heat in your cooling process, you could just transfer that heat, more like transport that heat, into the place where you need to add heat. So you don't waste that heat and then generate another heat to add. Now, let me give you an example in a commercial building. If you come to a commercial building, let me take a hotel, for example. You come to a hotel, for example, and you see that they have generator. A generator is running, maybe there is a gas generator or this is generator. Now you will notice that that generator has a lot of heat loss. If you add diesel into a generator, believe me, about 70% of the energy content of that diesel is lost in the form of heat and noise, right? Now, when you use about 30% or 35% to generate electricity, now you move that electricity into the building, and then you convert that electricity to hot water. So you use it to heat your hot water in the rooms, right? Now, it sounds funny because you have a lot of heat that is being wasted at the point where you're generating the electricity. You have about 70% or 65% of heat that is being wasted. What if there is a technology that you could use to collect that heat that is being wasted in your generation point, and then dump it into a hot water, and then pump that hot water into the hotel, whereby you don't need to convert that electricity back to heat, to hot water. I don't know if this makes sense. I hope some of you are able to understand what I'm trying to explain here. But that is where the concept of pinch analysis comes in. If a process requires addition of heat and another process requires removal of heat, it only makes sense that if you remove the heat from a certain process, you can transport that heat and then add it to the process that needs heat. So if you identify those two processes, it makes sense to bring them closer together so you can reduce the cost of moving the heat from point A to point B. You can bring them closer together so that as you're removing the heat from your cooling system, you're adding the heat to your heating system. That's the whole concept of pinch analysis. So let us talk about heat pump. So heat pump is like a reverse of your air conditioning system. It's like a reverse. You know, your air conditioning system have evaporator. Evaporator is what you have inside your house, and you have a condenser. A condenser is what you have outside your house. Now you will have noticed that when you go outside your house, that condenser is always hot. And what air conditioner do is that it absorbs the heat inside your room or inside your space and dump the heat outside through the compressor, through the condenser. It dumps the heat outside. Now, what heat pump do is that it compresses atmospheric air. Now, when you compress air, now this is a chemical process. If you compress air, okay, if you compress air, you reduce the volume of the air. What you actually do, you increase the pressure and you increase the temperature. That's what happens. When you compress air, you increase the temperature. So when the temperature is elevated, you can use air to collect the heat from the compressor and dump it into water. So heat pump is like, you have your air conditioning, just your normal air conditioning system that you have in your house. You have it, but now this is the hot area. This is your compressor, right? Now this is your condenser, which is hot, right? So what you do is that you can pass air around your condenser and collect the heat that is in your compressor and use that heat to heat your water, to produce hot water or drying air. For example, if your industrial process includes drying, so I've been to a sugar company, a sugar manufacturing company where they need to do drying. Okay, so this is just an illustration, an example. You could use this hot air to pass through your sugar to dry it. Instead of using another electricity or another form of energy to generate the heat for drying, you can use this waste heat to do your drying. Okay, so that's what, you know, this is a way of recovering waste heat from a compressor. And we know that a compressor produces coldness. I mean, sorry, your air conditioning system or a cooling system produces cold air, meaning that they extract heat, they remove heat to produce cold air. So as you're removing that heat, so at this point, you're removing the heat at this point, right? This is your evaporator, you're removing heat. And at this point, instead of dumping that heat into the environment, you recover the heat and use it for your industrial process. That's what heat pump helps us to achieve, okay? So this is just a way to categorize the efficiency of a heat pump. So heat pump is one of the technology that you can add. For example, you can add 4 units of electricity, 4 units of energy in a heat pump, and you can actually get like 12 units of energy out. So it has a positive impact. You're adding a smaller amount of energy, but you're getting a higher amount compared to what you put in. Okay, so we don't want to call it efficiency. And then there is now a concept for it. We call it coefficients of performance. And that's what we call COP, coefficients of performance. Okay. You can check the coefficients of performance of a heat pump, and you'll be seeing something like 4, meaning that for every unit of energy it consumes, it produces 4 units of energy output. Just 1 unit that you put in, you have 4 outputs. Okay, that's what it means. Okay, and that's what we refer to as coefficients of performance. And here is the formula. Now there's a coefficient of performance for cooling, and there's a coefficient of performance for heating. But most often, we use coefficient of performance for heating. When you're talking about cooling, we use energy efficiency ratio. Energy efficiency ratio. So if you look at your air conditioning system, you will see energy efficiency ratio. But if you look at a heat pump, you will see coefficients of performance. So here I just so this is energy efficiency ratio that I talked to you about. So if you're talking about cooling, for most times you talk about energy efficiency ratio. Now both energy efficiency ratio and coefficient of performance are used to to measure efficiency in cooling and heating systems. Okay, so the thing is this: sometimes you might be giving this efficiency ratio for air conditioning system, and you might be asked to convert it to coefficient of performance. So those are the areas in which questions might come in. Like most of this one I'm talking to you about now, basically for exams. You might not necessarily use them significantly in industries, but maybe for the purpose of passing your exams. So this is a relationship between coefficient of performance and energy efficiency ratio. Okay, so if you're given a problem and your answer, you're giving the factor, maybe you might be asked to calculate certain energy efficiency ratio, convert it to coefficient of performance. This is the formula you will use. Okay, so this is an example just to make us understand this clearly. So this is find the energy efficiency ratio of a heat pump having a coefficient of performance of 4. Okay, find the energy efficiency ratio of a heat pump having a coefficient of performance of 4. Now, like I told you, coefficient of performance is mostly for heat pumps. But somebody might say, look, I don't understand this concept about heat pump. I want translate it to me in energy efficiency ratio. Okay, so how do you convert it? So this is what you do. So you just pick this formula. You're already given the COP. You have the COP. So once you put it, you do your cross multiplication, and then you have your energy efficiency ratio. Now, energy efficiency ratio is not different from how you calculate energy efficiency ratio. It's not different from how you calculate efficiency in any system. So energy efficiency ratio is the cooling output. That is output. Efficiency is always output over input. Okay, but in energy, you're talking about cooling output over the power that you put inside. So there are two different units. Okay. Now, when you're talking about efficiency is a dimensionless unit. A dimensionless unit. Now, when you're talking about energy efficiency ratio, you also have to be very careful to make sure that the unit of your numerator is the same thing with your denominator. The unit of your numerator is the same thing as your denominator. So you have to convert both of them to a common unit. But I mean, this is something you can read up. The most important thing is what I have just highlighted here, which is this equation that you can use to convert from COP to EER. And like I said, this is just for examination purpose. Most often, you might not do all of this when you go to conduct industrial energy audits. So this is EER versus COP. Some of these you can read up. I'm skipping some of these because you can just read them up and understand. At the point where I need to explain, I'll just go down and explain and then illustrate. But for some of these things, like everything you're going to see here, I've already explained some of them already. I've already explained most of what you're going to see here already. So let's talk about building, heating, ventilation, and air conditioning system. Building heating. Now we call this for short HVAC. HVAC means heating, ventilation, and air conditioning. Okay. So sometimes you might hear HVAC. What it simply means is, heating, ventilation, and air conditioning systems. Now, HVAC is a significant energy user. I've seen a TOR for an energy audit. TOR means terms of reference for an energy audit. And one thing that they've highlighted is that they want the energy auditor to investigate SEU. They didn't write it in full, but they expect that whoever is reading that document should understand what SEU means. So SEU means significant energy users. So if you come to a commercial building, significant, so okay, let me ask this question. What is a significant energy user in a commercial building? Somebody can unmute his mic and then speak, his or her mic and speak. Just mention one significant energy user in a commercial building.
But, okay, in a commercial. HVAC system like air conditioning in a commercial building is boilers. Hello?
I'm hearing you.
In a commercial building, boilers.
Okay. Yeah, boiler is, yes, boiler. So which other one?
HVAC.
Which other one?
I say HVAC, like air conditioning.
Okay, fine, perfect. I know I didn't want to use HVAC. HVAC is too ambiguous, it's too generic. But when we say air conditioning, yes, that's it. So for commercial buildings, the most energy consuming equipment in commercial buildings are cooling system, the air conditioning systems. They're the highest. In our weather here, in tropical weathers like Nigeria and some other hot places. But if you go to other cold regions, it's heating. But in our weather, it is cooling. For commercial building, I specifically said commercial building. When you go to industrial buildings, it is not cooling. If you go to industrial buildings, can somebody tell me what consumes the most energy in industrial building? We will get to that, but I just want to see, how we can respond to this. In industrial building, what is the highest energy consuming unit in industrial building? Any attempts?
Heaters.
No?
Boilers.
Okay, let's not waste so much. We are eventually going to get to that, but it is motors. It is motors. For industrial buildings, it's motors. Then for commercial building, the highest energy users are cooling system for Nigerian weather anyway. So this is just a significant portion of building energy consumption is for HVAC. Either you're heating, which if you're in cooler region, you're heating. If you're in weathers like Nigeria, then you're cooling. Okay, so this is just for some country that have their details available. So the question: what induces cooling load? These ones are just basic knowledge. Like if you come to a space, what are the things that actually creates the need for cooling? Okay, so the things that actually creates the need for cooling are waste heat from lighting, from your machines, from your appliances, from data centers, even from human beings. Okay, it's also here. Human waste heat is about 70 watts per person at 25 degrees centigrade. So as a human, you release as much as 70 watts of power into this environment. That's why when you come out in a place that is crowded, the place is hot because there's a lot of body that is emitting heat into the space. And if there's not enough cooling system to remove that heat, and that's why you need cooling. You need cooling to evacuate that heat from the space into the environment. Okay, if you're not doing that, then the place becomes hot. So what can be done? A well designed, all these ones are just things you can do to reduce heating load. Now, these are basically for commercial buildings, okay? A well designed buildings can reduce heating and cooling load by up to 30%. The outcomes can be reached by adopting passive design features or construction measures. So for example, if you paint your wall, if you paint it white, most of us have a science background, and you know that white reflects heat. It reflects heat. But if you paint it black, what does it do? It absorbs heat. So if you paint the building, or if you paint the external surface of your building, if you paint it white, what it do? It will help the building to resist heat, to some degree, as opposed to when you paint it black, right? So that's why I say building. There's something we call double glazed window. It's very common in other world, Europe and America. Double glazed window. It's hardly seen in Nigeria because of the kind of weather we have. The roof insulation, if you enter a house that has POP, you will notice that it is cooler than buildings that without POP. You have wall insulations and all of. So these are just measures you could take to reduce inflow of heat into the building. So this is an example. This is Lagos, Nigeria, how they try to reduce the amount of heat flow into the building. And you can also see that the building is also tiled. They use tiles on the wall. Tile is also a poor heat conductor. Okay, so it can resist heat. You must have seen buildings like this where they use blinds. These ones are from Austria. Now let's talk about motor. Let's talk about motor. I told you that in industry, motor consumes the highest amount of electricity or energy in industry. So let's talk about motor. Now, motor is everywhere. Even your phone, you'll be surprised that your phone has motors. All those vibrations that you feel from your phone, they are being triggered by motors inside your phone, that causes those vibrations. So there's a lot of applications for motor. Motor is a mechanical system. It's for mechanical drive. It's used for mechanical driven systems, Yeah. So let's just move ahead with this. So 70% of commercial energy consumption is converted by electric motor. Motor efficiency plays a big role. All this, I will just leave them. I know I'm still going to somehow talk about them when I'm explaining, but these ones are just notes that you can read. So this is now for motor systems. You need to be very careful when you're buying motor. If you find yourself in a position to advise on the kind of motor to buy, you need to be very careful because the cost of buying the motor is insignificant compared to the cost of running that motor. So the cost, if you look at this, then now you can see energy consumption for the entire life of the motor. So energy consumption constitutes 95% of the cost. The life cycle cost of that motor, energy consumption constitutes 95%. So the cost of buying that motor, that's the investment, is just about 3%. So when you're buying a motor, it's very, very critical to look at the efficiency factor of the motor that you're buying, because every improvement in efficiency will save a lot of money over the lifetime of that motor. It might be slightly expensive, but if you look at the cost of running it, the cost of buying electricity to run those motors, you find out that you're saving far much more. So these are potential savings if you improve your motor system. You have a mechanical system optimization. We are going to discuss this. You have electric speed control. This is where we use something we call variable speed drive to achieve this. They have increased use of energy saving motors. Now, if you improve, there are different classes of energy efficiency motors. Okay, so if you buy a better efficient motor, you can save up to 10%. But most of the savings will come from your mechanical system optimization. Now, let's look at what goes into a motor and what comes out of a motor. Now, please, this is a motor, right? This is a motor. Now, what comes into this motor is electric power, right? Electric power. Now, what comes out of this motor is also what? Mechanical power. And this mechanical power is used to drive a load. When you go to industry, you see a conveyor, you see so many moving parts. What is actually, you might not see the motor, but what is actually driving all of those movements is motor that is somewhere that is moving those load. Okay, so now motor is used to generate mechanical movement to drive any load that you want to drive. Okay, so what comes into this motor is kilowatt electrical. What comes out of this motor is kilowatt mechanical. Please get this concept. What comes into a motor is kilowatt electrical. What comes out of the energy form that comes out of motor is kilowatt mechanical. So now the input, the kilowatt electrical, this is how you calculate the kilowatt electrical. If it is kVA, if it is someone's mic is on again. Please mute your mic. We don't have enough time. I need to quickly go through this within the shortest possible time, please. So now energy that goes into the motor is kilowatt electrical. So what is kilowatt electrical? This kilowatt giving electrical data is √3 times the voltage times the current times the power factor. That is active power or real power. Okay, but if you take away this power, now for this is a three-phase electrical system. Once you see √3 is a three-phase electrical system, but some motors are single phase, some motors are three-phase. So we assume that this is a three-phase motor, but most industrial motors are three-phase. Most heavy industrial motors are three-phase. So now this is the input. This kilowatt electrical that goes into a motor. Please note this. Kilowatt electrical that goes into a motor. Now, the output is kilowatt mechanical. Kilowatt mechanical, and this is the formula to calculating the output. So kilowatt electrical is what goes in, is equals, now this is input, and this is output. Now the output is kilowatt mechanical times load factor. Load factor. So how do you know the loading on the motor? What's the loading on? If the motor can do 100% work, how much load is placed on that motor? Is it 80%? Is it 70%? Is it 50%? So this is the load factor of the motor times the efficiency of the motor. Now, this efficiency of the motor and kilowatt mechanical, most often you find them at the nameplate of the motor. At the data page of the motor, you find this kilowatt mechanical and kilowatt and efficiency. Now, let me state here that when you see any motor and you look at the nameplate and you see the energy detail, like you see maybe output of the motor, you see kilowatts. please, it is kilowatt mechanical, not kilowatt electrical. That is output. If you see the nameplate of any motor and you see the energy output or whatever it is, and you see kilowatts, even if they put mechanical or not, whether they put mechanical or not, please assume it is kilowatt mechanical. That is output of the motor. And the reason is the input of the motor depends on a lot of factors. Okay, so they will always say the output, the work that that motor can do for you in terms of kilowatts, and it is kilowatt mechanical. So, so here is just further explanation of kilowatt. Now, this is the same formula we had in the other slide, right? Okay. So if you transpose it, so what we'll try to do here is try to establish this formula for both single phase and three phase. Remember, I told you that motors can be three phase, it can be single phase. So if you expand this equation, so we have kilowatt electrical, and we know the equation for kilowatt electrical. Now, this voltage times current times power factor is kilowatt electrical. Okay. So if we make kilowatt mechanical subject of the formula times percentage loading.
So you have to move. So
okay, I just need to mute everyone again. Oh, shit, we'll have everyone. Okay. Okay, so so if you make kilowatt mechanical, now this is kilowatt mechanical. If you make kilowatt mechanical subject of it,
don't go back there. So this is for good, but we'll come on the DJ team, we'll come on the barbecue team.
hello, Uche. Hello, Uche. Oh, this is becoming a difficult one. Hello, Uche. Just give me a moment. I need to handle this because he's also the acting as a host, and it's becoming difficult for me to put him on my end.
So we're removing the component of DJ. I'll give it to
I need to let him know he's interfering in our.
Like I said, it's not like this one. Spending a good day here to do this because I don't think we replace the song. So everybody's constrained to meet up the deadline. Are you getting this? They just this one. After this one, go back.
Okay, so let's continue. So what we are trying to do here is to establish the formula for both single phase and three phase. And what we are going to see here, we are trying to make kilowatt mechanical the subject of the formula. Everything that we've derived here is from this very formula. There's nothing new here. This voltage times current times power factor is kilowatt electrical. This kilowatt here is kilowatt mechanical times load, percentage load, that's this load factor, times efficiency. So that's what we have here. Then for three phase, the only thing that has changed here is 1.73, and this 1.73 is the √3. If you do √3 on your calculator, you have 1.73. So it's either you do 1.73 or you do √3, and this for three phase. So this for single phase, this for three phase. Please note these two formulas. Very, very important. So like I told you, so this is a nameplate. So this is a nameplate from ground force motor. So when you look at this nameplate, you will see they have configuration for sorry, let me look at this. Okay, now motor have different kinds of connections. There are some motor that have delta connection. There are some motor that have star connections. Okay, so these are for electrical engineer, but you also have to have a knowledge of this connection. Star connection is where you're dealing with a higher voltage. You're dealing with 400. In the Nigerian voltage, you have 400. Okay, so this motor can work in Nigeria because our voltage is 400. And that is higher voltage. Then you have delta connection. At a delta connection, you have that is normal household voltage, which is 220. In our own case, it's actually 230, right? So you can either do both of them, but this is the voltage range for connecting this motor. But they told you, they gave you a kilowatt of this motor. It is 1.5. So now the question is this kilowatt mechanical or kilowatt electrical? I hope everybody understands this already. What is this 1.5 kilowatt? What is it? Kilowatt mechanical or kilowatt electrical? Someone unmute yourself and speak.
Kilowatt mechanical.
Thank you very much.
Thank you very much.
So you can mute yourself now. So you can also see that they've given you the efficiency. The efficiency of the motor is what? 82%. So what they've told that at 82% efficiency, this motor will give you this kind of output, this kilowatt mechanical output at 82%. So it has already been giving you, and they even give you a power factor, which is cos pi, okay, of the motor, how it operates. So you can see all of these details from the nameplate of your motor. So these calculations are easier, are very easy, okay? So this is a sample question. A three-phase induction motor is drawing 12 amperes at 440 volts. If the operating power factor is 0.8, then just give me a minute. Give me a minute, please. Okay, sorry for that interruption. I quickly needed to switch over my power. So I don't know if any of you have tried to attempt this question. I should have said this before I left. So, but this, if you pick the formulas that we have, this is a simple question. Let me see, is it a single phase or three phase? Or did they state? Okay, they say it's a three-phase induction motor. So what that simply means that we are working with a three-phase equation. This is the equation we are working with. Okay, so you might want to write down this equation. You might want to write it down. So here we know what the amperage is. We know what the current is. We know what the voltage is. We know what the power factor is. Okay, and the total is a three-phase. Now the question is, if they say we should calculate the power that is drawn by the motor. What are they asking us to calculate? Kilowatt mechanical or kilowatt electrical? Someone should unmute and speak. What are we asked to calculate? Kilowatt mechanical or kilowatt electrical? Can someone unmute and speak?
Kilowatt electrical, it said is being drawn by the motor, not the
Perfect.
output of the motor.
Yes. So we are looking for so you need to understand the question first. You need to understand when you're being asked to calculate kilowatt mechanical or you're asked to calculate kilowatt electrical. So it's very important you understand the question before you can even attempt. So here is the equation. So we are looking for kilowatt electrical, and this is a very straightforward question. We've given the voltage, we've given the ampere, we've given the power factor. So just put in all of these values and then you calculate. So this kilowatt electrical. So this motor is drawing 7.3 kilowatts. That is what it is drawing to give out the mechanical output that it is giving. So the answer is A. So here is further example. You can do this on your own. Here is it. I have also provided the solutions. These are sample problems that you can solve. at your free time. So let me ask this question. This is a very tricky one, but it helps, it tests our understanding. That's the essence of it. It tests our understanding. So an induction motor rated at 75 kilowatts and 90% efficiency. Now, this is what the motor is rated. If you look at the nameplate, it is rated that this motor is 75 kilowatts and it is 90% efficiency. 75 kilowatt at 90% efficiency, and it is operating at full load, meaning that it is operating at 100% load. Okay. So what will that motor do? Will it deliver? What will it deliver, or will it draw any of these options in the choice, multiple choice answer? So let somebody look at it and tell us what the answer will be. An induction motor that is rated 75, and this 75 is rated at 90% efficiency. Okay. What will it do? Will it deliver 75 or will it draw 75? Let me make it easier for us. Will it deliver 75 kilowatts or will it draw 75 kilowatts? An induction motor rated 75. Now, when you see those ratings on induction motors, those ratings are rated at the given efficiency in that rating, in those nameplates, right? So when they say that the motor is rated at 75, it is rated at 75. When it is operating at 90% efficiency, that's when it will give you 75. If that motor operates lower than 90%, it will give you less than 75% output. And they told you that it is operating at full load, meaning that your load factor is 100%. So what will the motor do? Will it deliver 75 kilowatt or will it draw 75? Let me narrow the options for us. Will it deliver 75 kilowatt or will it draw 75 kilowatts?
It will deliver.
Perfect. It will deliver 75 kilowatt because that is the rating that the motor has been given. So these are more other questions that you can play around. I've provided the solutions. Okay, so let's talk about sleep. Let's talk about sleep in motors. Now, motor consists of stator and a rotor, right? So, you know, motor has two things. One is the bearing, one is the one that turns, and one is one that, you know, is almost like stable. The stator is worked through a magnetic flux and all of that. Those are, you know, the technicality of how motor converts electrical power to mechanical power, right? Now, in doing that, there is something we call sleep. Okay. Sleep is maybe if the rotor turns a certain number of times, does that number of times that it turns, does it translate into the shaft's output? Okay, so if there are differences in that, then there are sleep, which most often occur in motor system. And as an energy auditor, we need to understand that so that we can actually recommend, you know, first of all, we need to understand why the sleep is occurring and then recommend how to avoid it. So sleep is a percentage difference between the synchronous speed of the motor and the rotor speed. As the load, as load is added to the motor, the shaft slows down a bit and the sleep increases. Now, this is we should all be very familiar with this analogy that I'm about to give. When you start up your generator, you find out it is moving at a very high speed, but once you add loads to it, it stabilizes, it comes down. Okay, so that's why that's what he's saying, that as the load is added to the motor, the shaft slows down a bit and the sleep increases. So when you add loads to your generator, the sleep increases because of the load you have on it. The sleep will increase. Okay, so so we are going to calculate how to calculate. We are going to, you know, discuss how to calculate the sleep. So now motor sleep is equals to N is synchronous speed minus the rated speed divided by the synchronous speed. Okay, so now synchronous speed, how do you calculate the synchronous speed? Now the given speed will be given, but how do you calculate your synchronous speed? Synchronous speed is equal to the frequency times 60. Now, okay, frequency in Nigeria is 50, right? Okay, so the frequency times 60 divided by the number of pole pairs. Please note this, number of pole pairs. So if you are told that the number of poles are 4, then the pole pair will mean there are 2. Okay, unless they specifically mention that the pole pair is 4. But you tell that the motor have a number of poles, which is 4, know that the pole pair is 2. Okay. So now in short, in abbreviation, this is the formula for calculating the synchronous speed of the motor. So let us just do an example to help us understand this, how to use that formula. Now, for a 4-pole induction motor operating at 50%, at 50 hertz, the slip at a shaft speed of, let me pull this out. Now, the slip at a shaft speed of 1,450. Now, speed is measured in RPM, revolution per minute. Now, they told us that the speed is 1,450 RPM will be what? Okay, now they're asking us, what will be the speed? Okay, at 1,450 RPM. Now, look at the solution. We first of all have to calculate the synchronous speed. Synchronous speed means that the speed at no load. That's what synchronous speed means. The speed of the motor at no load. That is more like what the motor is rated. Okay. So now the synchronous speed is, we are given that the frequency is 50 times 60 divided by 2. Remember, I told you that if they're giving 4, if your pole is 4, you divide it by 2, that is pole pair, you know, to get the pole pair. So when we do this calculation, we'll have 1,500 RPM. So at no load, when you on your generator, when you on this motor, you don't have any load on it. It is running at 1,500 RPM. But the moment you add a load on it, it started working at 1,450. So the question is, what is the slip of this? Okay. So we need to calculate the slip. Now, the motor speed is 1,400 RPM. Now, motor slip is equal to synchronous speed minus the given speed divided by the synchronous speed. We already know what the synchronous speed is. We already know what the actual speed is. So if we do that, 1,500 minus 1,400 divided by 1,500, we have the motor slip is 3.3%. And that's the motor slip. Okay. So like I said, the lower the slip, the better the efficiency of the motor. So this is the second example. It's just similar to what we've done in the first place. You can practice this and let me know if there are questions. So remember, I talked to you about efficiency classifications of motor. Motor has efficiency classifications, okay? So these classifications are according to IEC standard. So according to IEC standard, we have 4 levels of efficiency classification. We have IE1, IE2, IE3, and IE4. Okay. So the highest of them is IE4. That is super premium efficiency. Okay. And then the lowest of them is just the standard efficiency. And this is just for your knowledge sake. So this is motor loading. Okay. Motor loading means how well the specified motor capacity and mechanical load are matched. If they say that the motor can do a 75 kilowatt work, how much load is it doing? How much work is it doing? If you give it 20 kilowatt work and the motor is rated 75 kilowatts, what is the percentage loading on that motor? Just looking at these 2 figures that I've given to you, you will just see that the motor is underloaded. But if you have a motor that is rated 75 kilowatts and you have a load of maybe 60 kilowatts, then it is loaded well. It is normally loaded. But if you have that motor that is rated 75 kilowatt and you're giving a load of maybe 74 or 70 or even 73 kilowatts, then it's almost overloaded. And that's what the motor loading is talking about. This is overloading. This is underloading. This is a normal loading. I gave you 3 instances now, okay, where I say if that motor is 75 kilowatts and you're giving a load of maybe 10 or 20 kilowatts, then you're underloading that motor. This is what it looks like. The motor has capacity to do a greater work and you're giving it a smaller work, okay? But if the motor is rated 75 kilowatt and you're giving it a load of 60 kilowatt or 55 kilowatts, then you've loaded that motor very well. But if the motor is rated 75 kilowatts and you're giving a load of 64, or even 65, you're giving a load of 74, or even 75 or 73, you're almost overloading that motor. So that's what motor loading means. And the point is this, as an energy auditor, we try to achieve this nominal loading. This last one, this nominal load. If you do underloading, you're going to there are inefficiencies and there are cost consequences. If you do overloading, there are inefficiencies and there are cost consequences. So it's going to be overheating. You're going to reduce the lifespan of the motor, and it may fail regularly. If you have underloaded motor, it will run at a fraction of its specified power and draws excessive and ineffective electrical current. As this current does not supply useful energy, efficiency is low. So those are just it. You can read all of this up. Voltage drop causes changes in motor. Okay. In our last session, last Saturday, we talked about voltage unbalances or voltage imbalance in motor system and how it affects motor. So it affects the efficiency of a motor, it affects the power factor, it affects the running current and temperature. So if motor terminal voltage is below the rated voltage, it will draw more current than rated current, which will ultimately result in overheating of the winding and thus reduces the lifespan of the motor. This is a very simple explanation. You know that power is equal to voltage times current. Power is equal to voltage times current. So what this is saying that if the voltage is low, what is going to happen for this motor will still draw the amount of power that it needs. But what is going to happen? It will draw excess current to compensate for the lower voltage. For all those of you who are electrical engineers, you understand this perfectly. But I'm just stressing this point for those of us who are not electrical engineers. Power is equal to voltage times current. If the voltage is low, the motor will draw excess current to compensate for that lower voltage. And once you do that, it will result to heating and, and of course, excess loss of energy will begin to occur. So when your voltage unbalance is 1%, it is okay, but if it goes beyond 1%, 1% causes unbalances and thus loses heat. Okay. In our last session, I talked about this voltage unbalance, and I explained how to calculate percentage voltage unbalance. Okay. Now this is now adding another layer to what we learned last week, and it's telling us that if you have voltage unbalance of 1%, it is okay. But if it goes beyond 1%, it begins to affect the efficiency of the motor. And here it is how it happened. This is a drifting factor, and this is your percentage voltage unbalance. So the higher the voltage unbalance, the higher the losses and the inefficiency of the motor. So what is beyond motor? Remember when I talked about motor systems, sometimes you might not save so much money by buying a higher efficiency motor. You save greater portion of the money by the thing that the motor is driving. Okay, how you manage the load, the output from the motor, and all of those things that the motor is driving. Okay, and that's what this optimizing potential for motor itself are rather limited. Much more can be achieved in the system that the motor is driving. Remember, I told you that motor is just driving some equipment. If you go to industry, you see some moving equipment, you might not see the motor. The motor is somewhere driving those equipment. So you might want to optimize those things that are being driven. So for example, anytime there is no load on those conveyors, make sure you put it off. You shut the motor. The motor does not run. When the motor is running, it's using those conveyor belts, and it is at low load. The load factor is low. You might want to introduce what we call variable speed drive to reduce the power that motor is drawing, because the load that it is powering is actually low. So these are the things you can do to improve the efficiency of the motor. You can use variable frequency drive. You can also use housekeeping measures to turn it off when it is not working. Low and high cost maintenance. So these ones are just maintenance of motors. Now let's talk about drives. Now we talked about motor. It's just like electrical system. You have generator and they have distribution system. The same way you have for steams, you have boiler and they have steam distribution system. Now when it comes to motors too, you have the motor itself. I have a drive. Drive is what transfers the mechanical power from the motor to what you want to drive, to those conveyors. Okay, so those are what we call drives, and we have different types of drive. We have belt drive. Our vehicles uses belt drive. We have direct drive. We have gear drive. We have chain drive. So we have different kinds of drive. So like I mentioned, drive is what transfers the mechanical power from the motor to what you want to drive. Okay, so these are, it is important to understand how this mechanical power is also transferred from the motor to the things you want to drive. And these are how you can also, these are measures you can take to lower the cost of your drive. So for example, if you don't have the right kind of drive, you might notice that you might need to change your belt. So for example, if your belt is not proper, you might need to frequently change your belt, or your drive might kind of induce sleep into your motor system. Drives can introduce sleep into your motor system. So you need to make sure that you use the proper kind of drive. So these are low and high cost measures for drive system. So let's talk about pump. Now, a question is, are pumps the same thing as motors? I just need one answer, then I'll take it off from there. We need to wrap up. We almost we have almost expended our time. So what are pumps, please? Are they the same thing as motors? One person, just think about it. Pumps, are they the same thing as motors?
No, I don't think so, sir.
So fine, fantastic. So pumps are not the same thing. So pump is a motor-driven application. Pump is a motor-driven application. So that pump has a component of motor and there is a pump. Okay, so just have that clear. They are not the same thing as motor. So this is a pump, right? And now the major component of a pump is the impeller. Impeller is the thing that actually pushes the liquid or the fluid. Okay, and on this we measure the demand of a pump in two ways. Pumping demand is defined by static height and dynamic height. Static height means the normal height, like if you're pumping from ground floor to third floor or to fourth floor or whatever height, that is static height. But we have dynamic height. Dynamic height are those resistances within the pipe, the flows, the bends, the walls of the pipe. Those are dynamic height. The resistance that the liquid or the fluid has to overcome before it reaches that static height. Those are what we call dynamic height. So this is an equation for calculating the powers of a pump. Now you can see kilowatt P. Kilowatt P is the shaft power. Now this kilowatt P is synonymous. It's almost the same as kilowatts mechanical. Okay. Now the reason why we might not use kilowatt mechanical is because kilowatt mechanical is shaft output from the motor. Shaft output from the motor. But this kilowatt P is what the pump requires. What the pump requires to produce or to pump certain quantity of water. So there could be changes. The shaft output could have deteriorated before it gets into the pump. Before it forms the kilowatt P, there might have been changes. Okay. So kilowatt P is the shaft power required to operate the pump. And this is the equation to calculate that. So I just want to. So the Q here is the liters per minute, and the H is the meters, the height you're pumping, and P will be the kilowatts of the pump. Okay. So important savings can be obtained by lowering the flow rates, reducing the head. If you're pumping from a ground floor to one-story building, you will need lesser amount of power than if you're pumping from the ground floor to maybe fourth floor. Okay, so if you lower the head, the height, you reduce the power that is required. Okay, so another thing is lowering the flow rate. If you lower the flow rate, of course, the power that is required will reduce. Then operating the pump at best efficiency point of the pump. So this is an example of calculating the power of a pump system, of a pumping system. It's a straightforward question. You can look at it. But one thing I also want to talk about pump here is the affinity laws. How does the quantity that is being delivered, the quantity of water that is being delivered, how does it relate to the power that the motor is or the pump is drawing? How does it relate with the height? How does it relate with the speed of the impeller? How do they relate? So that's what affinity laws help us to understand. So affinity laws say that the first affinity law say that now, remember I talked about the impeller, which is the main component of a pump, right? Now, impeller have diameter, and the diameter is, from this end to this end. That's the diameter, right? So you can increase the diameter, you can reduce the diameter. You will believe me that if you increase the diameter, you have more flow. But having more flow means that you have to add more power to drive it, right? So affinity law helps us to understand the relationship between all of this. So assuming that you have a constant diameter, you kept the diameter constant, right? How does it affect energy that is drawn? How does it affect the quantity of water that is delivered? Okay. So now the quantity of water that is delivered or the quantity of fluid that is delivered is directly proportional to the number of rotational speed of the impeller. Okay, N is the rotational speed. I've defined all of those here. Okay, N is the rotational speed. Q is the flow rate or the flow of liquid or fluid. Okay, so the flow is directly proportional to the rotational speed. If the speed increases, you have more flow. It's just a common sense. Okay, now there's another law relating the height you're pumping to and the speed. So the height is directly proportional to the square of the speed. Square of the speed. Okay. Now another relationship is the power consumption, which is the P. Okay. Now the power consumption is directly proportional to the cube of the rotational speed. To the cube of the rotational speed. Okay. Let us see an example with that. Now a centrifugal pump is delivering 200 meters cube per hour. Now this is the flow. The impeller diameter is trimmed, so you reduce the impeller diameter from 10%. Okay, you reduce the impeller diameter by 10%. So you can assume that the impeller diameter is 100%, and if you reduce it by 10%, meaning that it's now come down to 90%. So P1, sorry, the D1, the first diameter is 100. The D2 is 90. They didn't say that directly here, but that's what it means. If you are reducing anything by 10%, it means that there is a 10% reduction. You can decide to use 50 and 40. You will arrive at the same answer. Okay. So now the flow, which is the meter cube per hour, will be what? Now, what they're asking us, if you reduce the impeller diameter, now this is the impeller. If you reduce this impeller diameter by 10%, how will it affect the flow? How will it affect the water that we're going to get or the fluid we're going to get at the other side of it? And that's the question it's asking us. Okay. So in this case, we know what the Q1 is. Q1 is 200. That is the initial flow. Okay. It's 200 meters per hour. We know what the initial diameter is. We use 100. You can use 50. Okay. But if you're using 50 minus 10% will give you 40. So your D2 will be 40. So our initial diameter is 100. Our second diameter is that you are reducing it by 10%. That's our new diameter now is 90. They're not asking us for the flow. That is Q2. Okay. So what we are going to do, we go to those equations and see how the flow is related to the diameter. That's the diameter of the impeller. I'm sorry, there is something I skipped here, but maybe I assume that you also understand it when you read it. You know, in this first instance, we kept the impeller diameter constant. There is also another instance where we keep the rotational speed constant. That the speed of this impeller diameter, will keep it constant. And we still establish the relationship between the flow and the diameter, the height and the diameter, the power consumption and the diameter. Okay. So that question is actually asking us for this first equation. The flow, if you reduce the flow from 100, if you reduce the impeller diameter from 100 to 90, how would it affect the output, the flow rate? So we'll take this first equation and we substitute. So that is the equation we have here. We know our Q1, which is 200. But we don't know our Q2. And this Q2 means that if you reduce the impeller diameter from 100 to 90, how would it reduce this output? Okay. So we know our initial diameter of the impeller, and we know the final diameter of the impeller. So when we do that, our Q2 will be 180. So if you reduce your impeller diameter from 100 to 90, you will reduce the flow that you're going to get from 200 meters per hour to 180 meters per hour. Sorry, 180 meter cube per hour. That's what it means. So I've also explained that interpretation here. Okay. So these things are just basic. like this pump affinity laws, they're just basic. I believe that when you also study it on your own, you understand perfectly how to use it. But if there's any confusion, please reach out to me. So these are issues with sometimes you might oversize your pump, which is not also a good thing. So you might look out for, if you go for an energy audit, see areas where a pump has been oversized. And how do you know when a pump is oversized? Okay, you see excessive flow noise, you have frequent replacement of the bearing. So you can ask questions to have an indication when the pump is oversized. So now this is parallel and series connection of pumps. So when you connect pumps in series, excuse me, when you connect pumps in series, what you're actually doing that you're not going to increase the volume, the flow rates. You're not going to increase the quantity of water you get if you connect them in series. So this is just if you're designing a flow system, okay, and you want to get certain quantity of fluid delivered at certain ends, okay, you have to know how to design it. If you design it in series, you're only going to increase the head, that is the distance. If you're pumping water from Lagos to Abuja, okay, one pump might not be enough. You might need to connect them in series. You might need to connect from Lagos to Ogun State. You put another pump in Ogun State to transport it to maybe Oyo State. If connect another pump, so that is series connection. You only increase the distance, but you cannot increase the volumetric flow. Now, if you want to increase the volumetric flow, you connect them in parallel. They have a higher number of flows. So that's what series and parallel connection of pump means. So this is how to optimize pumping system. So you notice if you go to some industries, they will use pumps to pressurize water. They will not have valves, to throttle it. This might not really make sense unless you have a practical experience maybe in an industry, right? Yeah, but if you increase the pressure of pump and then at the output end, you now use a valve to also reduce that pressure, it's a waste of energy because you use energy to raise the pressure, and where you needed it, maybe you need the water to, so for example, you need the water at 4 bar, for example, the pressure is 4 bar, and then your pump is producing that water at 7 bar. What it means that you need a valve to reduce that 7 bar to 4 bar before you use that water. And that is a waste, energy waste. So you need to look out for, if you're looking at pumping system and it's for an industrial process, you need to find out at what pressure do they need the water and make sure that the pump is producing that water at that pressure. So you might also use VSD, variable speed drive, to control the speed of a pump. So this is variable speed drive, variable frequency. Now, variable frequency drive and variable speed drive, they all mean the same thing. So these ones are just the advantages of using a variable frequency drive or variable speed drives. All these are just advantages, HVAC components. Now, these are just HVAC. Like when we talk about HVAC the other time, HVAC can be cooling, it can be heating, okay? So these are the cooling side of HVAC system. Most buildings, you see some of this HVAC. This is just pictorial illustration of HVAC systems. Now, but there's something that I want to talk about. In commercial buildings, there are 2 kinds of HVAC systems. You have continuous air volume, and you have what is this other one? I'm struggling to remember the name. Okay, so there is constant air volume and there is variable air volume. Constant air volume means, I hope I've not missed something. Okay, so there is constant air volume system in HVAC. If you go to most of these commercial, all these high-rise buildings, you don't see the air conditioning system in the individual rooms. They have a central air conditioning system. Hello.
Please help us with time. We have other classes.
Yeah. Sorry, I'm running up in the next 10 minutes. Sorry, I know, I noticed that in the next less than 10 minutes we'll run this up. So, but the continuous air volume means that you have a compressor that is cooling the air, and when it comes into the space where you need it, if you don't like the cold air, there will be another thing, there will be another heater at the room to heat it up. If you see what has happened, if you look at the cycle, there's a compressor that is cooling it and it brings it to your room, but you don't want the cold air, you want it hotter. You now have another heater to heat up that air again. That is a waste energy cycle because you need energy to cool it and you're not using energy to heat it up again. And that's a very bad or a very bad system. It is no longer in use mainly, but you might still be able to find it in some commercial buildings. But there is variable air volume system. A variable air volume system means that there's a compressor that cools it. When it comes to the room where you need to use it, there is something that we call damper. Damper regulates the amount of air that comes into your space. Okay, so it's variables. It's not a constant air cooling. So these are the two different things for central cooling systems. This compression cooling, I'm sure most of us already understand how compression cooling is. I'll explain this when I talk about heat pump. When I talked about evaporator, I will talk about condenser. You have expansion valve and you have compressor. I've explained this already. This is waste heat recovery. I think I've also explained this when I was talking about heat pump, where you need to recover the heat from your compressor and you can use it for your industrial processes. So this is exactly what we're talking about. So key optimization approaches. I also talked about combined heat and power. When I made an illustration about a hotel that generates electricity and the 70% is wasted as heat, and they take 30% or 25% into the building and they use it to generate heat, which is the hot water. So this combined heat and power can actually solve that kind of problem. So imagine that you're generating electricity with 30% and the remaining 70% that is being wasted, you now use heat exchanger to collect it and heat water. Okay, what you've actually done, what we call combined heat and power. You're producing power and you're producing heat. That's what combined heat and power simply means. So these are the ways to optimize it. So there is something we call compressed air system. I think this is the last part of this presentation. There's something we call compressed air system. Most industrial tools, they are pneumatic. When I say pneumatic, meaning that they use compressed air to work. Instead of electric, some use pneumatic processes. So for those industrial processes that uses pneumatic pressure to work, you need to generate compressed air to operate all of those equipment. And that's where compressed air system comes in. Now, compressed system is the most expensive air. It's the most expensive energy, form of energy. And the reason is because 73% of the electricity, okay, now this is the life cycle cost of a compressed air system. But here is what I want you to understand. If you more than 80% of energy that goes into compressed air is wasted. More than 80%. Remember, we're talking about the generators. We are talking about maybe about 70% that might go into waste heat. But we are talking about compressed air system. You're talking about more than 80% of the energy that you put into a compressed air system that is being wasted. So it's the most expensive form of energy. And it should not be. So when you go to an industry to conduct an energy audit, you need to pay attention to air leakages, the compressed air leakage. If you notice air leakages anywhere, you have to recommend measures for them to stop it. Because the smallest amount of leakage can compound into a big amount of money in providing the energy to provide that compressed air. So it is very, very important to look at that. And in compressed air system, there is high opportunity to recover waste heat. Waste heat. Compressed air system has a waste heat area where you can actually recover some of this waste. So that's 80% that is being wasted. Most of them are being wasted as a waste heat. So you have to see opportunity to recover those waste heat. And that's what you can see here. This is the amount of energy that goes into a compressed air system, and this is waste heat that goes out. Okay. There are leakages, there are actuations, but in the end, you find out that the tool or air that you need to power is just using very small amount of energy. Right? You go to some industry and you see people using compressed air to clean their body or to clean the equipment. Okay. It is not good. They can actually use a blower. A blower is cheaper. A blower will give you pressurized air, not a compressed air, and it's cheaper. But if you use a compressed air, that's very expensive. If you need to use blower to clean up any surfaces, it's cheaper than using compressed air. So that's an alternative. If you see people using compressed air to clean up surfaces, you can use blower, not compressed air. So these are 7 opportunities from a compressed air systems. And compressed air system measures, repair leaks, frequent repair, replacement filters, heat recovery, optimization of compressor. Yes, compressed air system have compressor that compresses the air, and that's where the source of waste heat is coming from. So use of VSD, variable speed drive. So these are all measures you can take. Low cost measures, these ones you can read up, and that brings me to the end of this section. Sorry, at some point it appeared that I'm trying to rush through it. I just needed to cover up the time. And like Engineer Uche will also tell us that what we are doing here is to guide us and make us understand the things that we need to learn or the things that we need to do, more effort is required on our individual side to actually understand these things fully. Okay, so with this, I've come to the end of today's class. And I don't know if I have any question, comments, or suggestion. Question, comment, suggestion?
Okay, sir.
So
thank you very much
okay.
for the class. Yes, I actually have a question and a suggestion. Question is, you talked about synchronous motors, but what about asynchronous motors? I know something like that exists, right? What are they, if I may ask? And the second one is, it would really be nice.
Sorry. What did you ask in the first one? Say that again, please.
Asynchronous motors. You talked about synchronous motors, but I have heard something about asynchronous motors. It's just an A in front of the synchronous. So what are those, and are they applicable? You know, to.
I'm sorry, I didn't understand the question. You said there is I didn't get that clearly.
No, you said there are synchronous motors, right? Synchronous motors. When you were talking about motors, then I said I've heard of asynchronous motors. That is with an A in front of it.
Okay, synchronous and asynchronous motors.
Yes. What are the asynchronous motors? Are they applicable? Because you didn't mention them in your presentation, sir. So I just want to know: is it that we don't use them in this part of the world or something? That's the question, sir. And then my suggestion is that. Hello.
I'm hearing you.
Okay, is that it would really be nice if you could give us the materials for the week in time before the actual day. You know, like the materials for this one here, it has not been posted in the group before.